In this lecture, we will briefly talk about drug metabolism and its kinetic modeling. So the modeling approach is very similar to the Hill equation we were deriving for the hemoglobin saturation ratio. It's the similar structure that you have binding and unbinding, and then you have reaction can go forward and backward. So in biological modeling and involving like reactions, those are a typical tool. So I'm not going to like go through this type of modeling again. It usually involves like modeling the binding with enzyme and these type of things. Um, you can look it up from the different resources. So what I'm going to introduce you is the result of the modeling, and you will see that this type of model is called like Michaelis-Menten equation. So as a result of the Michaelis-Menten modeling, or you just consider um enzyme like binding and the production and use the chemical reaction, and you will get the rate of metabolism. Metabolic rate is V max C total divided by Km plus C total. As you can see, the result is no difference compared to a bunch of similar equations we have seen before. But I do suggest that you try to derive it on your own, try to live it on your own, and just to get to the like practice. So what we're going to discuss today is look at this result and see like the limits, like a high concentration limits versus low concentration limits, and then what's the implication of how can we estimate or say something about the metabolic rate. So let me go through the again give you a list of the names, what they are. So Vn, Vmax is the maximum rate of metabolism. Maximum rate of metabolism. And the Km is we call it like a Michaelis constant because it's a Michaelis-Menten model. So it's a Michaelis constant. And hopefully by now you have seen this enough. So you know that the value means at which if the concentration is the same as this Km, then the metabolic rate is half of its maximum. Hopefully you can recognize this. Okay, so now let's see some limits, because you know that this if you draw R as a function of C total, this type of behavior. So let's mathematically analyze this. In the first scenario, if C total is much less than capital Kn. By the way, this type of analysis is the same for all the other similar models we discussed earlier. Earlier, we didn't like talk about this. We can talk about the same thing in an earlier lecture as well. So that means you know that what we discussed today would be applicable to all types of Michaelis-Menten model or models involves Q equations, field constant, these type of things. So if you look at denominator, you have two constants. So one constant plus the variable you are looking at. So now the variable we are looking at is the C total. So if C total is much less than a constant, and what it means is constant plus C total would be almost the same as the constant. So that means the rate of metabolism, metabolic rate, is approximately Vmax divided by Km and multiplied by C total. You can call this ratio Kmax divided by Km. You can just give it another name. Doesn't really matter. We call it little k, metabolic multiplied by C total. And also just make sure that we know what we are talking about. The K metabolic is defined as Vmax divided by Km. So the reason we give it another name instead of using the ratio Vmax divided by Km is just wanted to make it look more like informative in case that this is a linear in C total. So this is linear in C total. And this type of linear relation, we give it a name, we call it like first order kinetics. First order means because the linear in C total, so if you think about the exponent, so it's like C total to the power of 1. And that's why it's called like linear. And this is for very small C total compared to Km. So it's corresponding to a region like you have a very small, like small. So this is C total. Much less than Km. You can see that this line start to take off. So it's almost like you can fit it with a linear line. So this slope is little k metabolism. And this is the first order approximation for low concentration. And on the other hand, if C total is much larger than Km, then we have Km plus C total is approximately the same as C total. So now your metabolic rate is approximately Vmax multiplied by C total divided by C total, just equal to Vmax. It's a constant. And this is a constant. This is called like a zero order kinetics. We call it zeroth order because if you think about it, if you want to multiply by C total, it's the same as multiply by C total to the power of 0, because to the power of 0 gives you 1. And that's why it's called zeroth order kinetics. Let's just remove these. Okay, so now you can see for large C here, this is a region for C total much larger than Km. And at this range, so this is a range for small Km. This is a range for small C total. This is a range for large K total. And you can see at this range the plateaus, which are constant. This constant value is Vmax. Great. Okay. All right. So it tells us under some scenarios you can, for example, under low concentration you can linearize it, or under high concentration you can approximate it with a constant. And the reason sometimes people like this approximation is usually people may use the metabolic rate R as a part of another larger model. And if it's nonlinear in C total, you can see the metabolic rate is a sigmoid equation. It's nonlinear in concentration. And then mathematically, if you have a nonlinear equation, it will make it harder to solve analytically. So in order to get the intuition of what happens, people wanted to derive things analytically. And one way of doing that is to consider, okay, if we are at a low concentration region, we can simplify it. And at the larger concentration region, we can also simplify it. And then they can derive analytical solutions either in low or high concentration regions separately. And then they can interpret the results from the analytical solutions. So that's one way to look at it. So the metabolic rate saturates. That means at an extremely high concentration of drug, the body can only do at a rate at V max. That means when people prescribe a dosage of drugs, they need to be careful. So if drug is persistent in the body for a long time, they may be harmful for the body. So we want the body to have a mechanism to handle it, to metabolize it. And however, if the dosage is too large and the metabolism rate actually caps, so that can potentially leads to some drug toxicity. So this is something you may just want to be aware of. And also, we are talking about a regime, but in many cases, you may have, like, if C total is comparable to Kn, then in this case, you are not in any region. And in reality, when people start take a drug at the beginning, when the drug was initially taken in the body, it may have a high concentration in the body. Then at that time, it may take a zeroth order kinetics for the metabolism. And as the drug is slowly, continuously removed from the body, secreted from the body, it will continuously transient until it drops to almost zero, drops to a linear first order kinetics. So in between, there is a continuous transition. So continuous. And then in this region, you probably cannot use this is oops. What did I do? I want to change the color. Okay. So this is continuous transition. And within that region, probably you cannot do this type of simplification, and you might need to use the original nonlinear metabolism, metabolic rate, just to capture the dynamics. All right, let's look at a problem, leave it as a homework problem. So This problem says a drug is metabolized in the liver following Michaelis-Menten kinetics. The maximum metabolic rate is given. The Michaelis-Menten constant is also given. Calculate the metabolic rate when the total drug concentration in the plasma is A or B or C at 3 different C total level. Determine the kinetic order that best describe each case. So you are going to calculate the 3 concentrations and then discuss which region they belong to and explain like why you draw this conclusion.